Why, how does solid rock become molten, right? Why and how does solid rock become molten? We've talked about magma being there. Well, why is it there? Right? Now, within the asthenosphere, thin films of melt exist along the grain boundaries. And just to recap, remember the lithosphere, that's the crust and upper mantle, that's the rigid part of the tectonic plates, whereas the asthenosphere, that's the mantle below the lithosphere. That's the part of the mantle it's still solid, but behaves a little bit more fluidly. It's what convects, it's what flows, it's what the lithosphere basically floats on top of, right? So within the asthenosphere, I said it's mostly solid. But liquid has to occur down there somewhere, right? And it typically doesn't occur in these huge chambers as we think of them. More often, it's just in thin films that exist along the grain boundaries, right? So just a little bit of liquid, a little bit of magma in between each of those solid grains. And because the liquid forms in these thin films, surface tension actually keeps that liquid down there and causes it not to be able to rise. It's stuck to those solid grains, basically. Now, wherever that thin film is determines what composition it's probably going to have. Basaltic magma tends to come from the upper mantle, and most but not all of granitic magma comes from the lower crust. So the deeper you are within Earth, more likely the more mafic it's going to be, the less silica you're going to find. Now, how do we know what rock is like down in the mantle if we can't get there? It's physically impossible for us to send humans down there or sensors down there or dig a hole that deep. It just gets too hot. So we can't actually physically go there. How do we know what rock is down there? Well, we have to wait for that rock to come to us. And that happens often from volcanoes, right? So rocks that are from the mantle will get caught up in a volcanic eruption, be exploded out on the surface of the earth, and then we see those mantle rocks. And we call those rocks xenoliths, right? They're those really deep, solid rocks that are brought up in a volcanic explosion. They were never magma, they were never melted, they just stayed solid the whole time until they came up to the surface of the earth. The most common xenolith from the mantle is the rock called peridotite, and it consists mostly of three minerals: olivine, orthopyroxene, and clinopyroxene. And that's why it has that green color. That olivine gives it that green color. It also includes a little bit of feldspar, right? And some metallic minerals like magnetite. So it's often highly magnetic. So you can identify this rock from its green sheen and from its often being magnetic. And if you had a thin section, you could identify olivine and pyroxene and a little bit of feldspar. All right, now let's get into these phase diagrams, looking at how solids melt. At what conditions do they need to melt? What temperature, what pressure causes them to melt? Right? Now, the mantle peridotite can start to melt around 600 degrees Celsius, right? So incredibly hot, peridotite can start to melt. And we're going to walk through some different ways that rocks can melt using this diagram. There's a lot happening on this diagram, so let's orient ourselves first. So notice that the x-axis is temperature. The farther to the right you go, the hotter it gets. The y-axis is depth, meaning the farther down you go, the deeper you go, and the higher pressure you get, right? And there's a lot of lines on here. Each of these lines show a different thing. That dotted line that's labeled the geotherm, that's the temperature distribution within Earth. So notice that temperatures are very relatively cold at the surface of the Earth and then get hotter and hotter and hotter as you go deeper and deeper and deeper into Earth. That's the geotherm. Okay. The solidus, there's two solidus lines here. One is the other dashed line, and the other one's that really thick, bold line. Notice they're both labeled solidus. And that is the temperature at which the very first melt appears, right? So if you had a rock and it started to pass just to the right of those soliduses, and we'll explain why there's two of them in a bit, it'll start to melt. And then the liquidus is when it's totally melted, right? So for example, a rock that is 200 kilometers deep and 2000 degrees Celsius, it'll have started to melt. There'll be melt there, but there'll still be some solid pieces. It won't be all the way melted until it gets hotter and hotter and hotter and actually passes that liquidus. So temperature increases quickly with depth in the lithosphere, but is more constant in the asthenosphere. Notice that the slope of the geotherm is more close to horizontal in the lithosphere. The thing gets basically vertical, doesn't change very much in the asthenosphere. Why do you think that is? Well, that's because of mantle convection. Mantle convection in the asthenosphere is basically mixing up the temperatures and causing temperature within the asthenosphere to be more constant. All right, so why does the melting temperature increase with depth? We know that temperature increases with depth, but so does the melting temperature. So the deeper you go, the harder it is to melt a rock at any given temperature. Why do you think that is? Right. Well, that's because of the increased pressure, right? Solids are solids because the atoms within them are packed tightly together, right? Which means if the pressure is intense, something that is incredibly hot can remain a solid just because that pressure is keeping its atoms tightly packed together. All right, now looking at that anhydrous solidus, you'll notice that there are two little cusps, two little tick points at depths of 20 kilometers and 70 kilometers. What do you think, what might cause those little cusps within the anhydrous solidus, that bold line? That's caused from a change in rock composition at those depths, right? Each rock has a different composition, and each composition impacts at what temperatures it melts and freezes, right? So at 20 kilometers and 70 kilometers, that's where the composition changes in the lithosphere. The composition change of peridotite from plagioclase to spinel to garnet bearing, and those compositional changes affect the melting temperature. I also want you to notice that, again, there's two soliduses. One is a water-saturated solidus, and one's a anhydrous, meaning no water, solidus. And notice that when rock is saturated in water, it has a lower melting temperature. So it's easier to melt rocks when they contain water than it is when they're dry, they're anhydrous. And we're going to discuss why later.